Okay, so we have discussed about in the previous chapter about mechanical properties, and the chapter before previous chapter we have discussed about the defects, yeah, the defects, and the solidification and imperfection. Oh, sorry. After that, we have actually also discussed about diffusion. Diffusion is one of the mechanism that uh, is used in many of material processing, including for making alloy or making or controlling the defects in a material. Then in the previous chapter we discussed about deformation among others, yeah, deformations, extension of material, and we have discussed about plastic and elastic deformation of material. In the plastic material, it is where we have permanent deformation. So when while elastic, we have reversible deformation. When the deformation is still in the elastic region, whenever the load or the stress is released, then the material can go to its original shape or original size. On plastic deformation, on the other hand, um, the stress, the load is such that the elongation that occurs or the deformation that occurs in the material is already beyond its elastic region. Slips occurs, yeah, the slip between the planes occurs, and when the load is released, while the distance between the atom may come back to its original state, however, the slip cannot come back to its original state. Yeah. The slip between the planes are permanent uh, deformation. So this makes them to still in that plastic shape, plastic deformation shape. The deformation that occurs cannot be reversed. Yeah, so it makes permanent deformation. So from macroscale point of view, we call that as the yield strength or hardness. And this, which are a measure of material's resistance to deformation. How high of the stress that the material can withstand before it enters to the plastic region. And hardness indicates how high of the stress before the material can be completely broken, yeah, or failure. Okay, so these are mechanical properties that we can measure in a macroscopic scale using certain equipment like the tensile strength, tensile stress device. This deformation we can observe is in the macro scale. But what actually is going on in the microscopic scale? Of course, we have explained that the plastic deformation occurs due to the slippage between the planes in the crystalline structure. The net movement of large numbers of atoms is in response to the applied stress. So in microscopic scale, also this deformation involves movement of dislocation. That's why later we will see that when a material has dislocation or has defects, then it will be easier actually to for that material to deform, and the yield strength will also uh, be decreased. Yeah, be decreased. But later in the strengthening mechanism, you can also have a mechanism where this defects or dislocation can be made to be entangled to each other. So they will stack and lock to each other. So which will strengthen the material so that when upon the application of stress, they cannot deform easily as before. So it means that the yield strength is made to increase. Okay. So in this chapter, we are going to see how the strengthening happen, how that with certain process either mechanical process or thermal process, we can manipulate the mechanical properties of the material. We can make the material to be stronger. Also, we can make the material to be weaker, depending on the application. Not necessarily for every application, we want to have strong material. Sometimes we want to have plastic, we want to have elastic material, easily deformable, yeah, easily formable. We are going also to see why some materials are stronger than other materials. Sometimes even though they are of the same type, the same element. Then how can one manipulate dislocations and their motion? So by manipulating this dislocation and their motion, then the mechanical properties can be adjusted. So in metals, yeah, as we know, the metal bonding, the bonding occurs very weak actually because it is maintained by this electron cloud that can transfer from one atom to another atom. That's why this location motion is easier since in metallic bonding in metals, it has non-directional bonding. The metal clouds are everywhere without certain particular direction. For slip, it occurs in the close spec direction. Okay. So as we have learned in metallic bonding in chapter 2 or chapter 3, yeah, there is this electron cloud, and which is basically can freely orbit between these ion cores, yeah, which have positive ion, positive charge. In ceramics, however, which has covalent bonding, they are usually very strong. They are stronger than metals because covalent has directional bonding, okay, directional and angular bonding. And for example, in some material like silicon or diamond, which has tetrahedral bonding, or the atoms are completely, the valence shell are completely filled, and so they bond with the perfect crystalline structure, then they are very hard, very difficult to break this material. In ionic ceramics, yeah, like sodium chloride, the salt, it is also very hard, yeah, because it binds with this very strong electrostatic binding, okay, and it needs to avoid when we do motion, the motion needs to avoid the positive and negative neighbors, okay, because if it meets the same charge, it will be repelled, so it cannot move easily. So from these types of bonding, we can now understand why metals can be easily formable, right? Can be easily bent. If you have spoon, for example, you can bend with relatively, with of course with some force, but it's relatively easier compared to if you try to bend, let's say, tile, yeah, floor tile or wall tile. You cannot bend them. If you apply exert more stronger forces, it will not bend, but instead it will just break, right? Tile are basically ceramics, and usually they are ionic ceramic or a little bit of covalent. So either way, it is still strong. Yeah, even covalent bonding or ionic bonding, the ceramics are usually strong, and they do not formable or bendable as easily as metals. So dislocation motion, yeah, dislocation and plastic deformations are very much related. So when we see from external point of view, from macro scale point of view, when a material deform, yeah, like we mentioned metal, when metal is bent and it deform, what happens is that some dislocation within that metallic structure is being moved, yeah, from the for example maybe in the middle, and it will go to until the edge of the material such that then the deformation can be easily can be seen from outside, from external point of view, from at macroscale point of view. So in cubic and hexagonal metal, plastic deformation by plastic or shear or slip, in this case, one plane of atom will slide over adjacent plane by defect motion, by the dislocation motion, by dislocation or the motion of the defect. Yeah, for example, we have here this crystalline structure, and there is this edge dislocation line. One plane is missing, so you have this structure that attracted, yeah, in this part, because try to balance this vacancy, yeah, because of the missing plane, the energy tries to balance such that the energy is minimized. So when you apply shear stress, yeah, at the side to the right, you apply shear stress means that either one part, one plane is being fixed, then you apply on the upper part, so it will be like tilted, yeah, or you apply from both sides. In this case, from the left, from at the upper part of this crystalline structure, from the left to the right. At the bottom part, force is applied from the right to the left. Okay. Then what it does is this plane will slip. Okay, to for example here, yeah, this one will binds to the plane A. It becomes like this, and now the dislocation, the plane, so the plane defect, yeah, the plane defect will move as if it moves. Actually, what move is the slip plane. Yeah, so now the defect plane is here in the line of this plane B. Then this move further to C and then move to D. Yeah, this dislocation line, this edge dislocation line. Eventually, it will come out like this. There is no more plane here. Then it will come out to the edge, where you will have a unit step of slip. One plane will be coming out of the edge. So inside the material, it will be perfect crystalline structure because the edge dislocation line has moved to the edge. And what we will see from externally is that that thing, that material has deformed, okay, has some deformation. So if this dislocation doesn't happen, then deformation could not occur. So we can see deformation because the dislocation inside that material, the defect inside the material move, or what we call as dislocation. So dislocation motion produces plastic deformation. The bonds are incrementally broken and then reformed. So like this, the bond here is broken and then form at this plane. And then move further, this one, the bond, broken and form in with this plane. So what we see is that the edge dislocation seems to be moving from left to right, while actually the bond is between the planes are the bond between the planes is broken and then reformed to the left. Okay, so if this is the shear stress, at the upper part is from the left to the right, and the lower part from the right to the left. The plane here will slide to the right until the dislocation moves to the edge, where we see it as a unit step of slip. Okay. So, for example, this is occurs at plastically stretched zinc single crystal like this. So we will see this edge or unit step of slip at the edge of the material. Yeah, as this kind of what do you call it? Terraces. Yeah, terraces of slip. If dislocation don't move, plastic deformation doesn't happen. Now the question is, how do we generate this dislocation motion? So when things deform like this, it will move by applying force. It will move until going to the right. Okay. So this is from at the zero when we do shear stress. The upper part is moved to the sigma is to the left. The lower part, the sigma is to the right. Okay. So what will occur eventually is that there will be dislocation motion. Okay, this is the initial state. And eventually the material here at the left side will have one plane extra, yeah, on the upper part. While here on the lower side, it will have one plane extra at the right part. Externally seen, from external point of view, we see that the whole shape has deformed. The motion of single dislocation across the plane causes the top half of the crystal to move, or we call it to slip, with respect to the bottom half. But we cannot have to break all the bonds across the middle plane simultaneously, which would require a very large force. The slip plane O0 and O1, this one is the crystallographic plane of dislocation motion. So in 3 dimension, multiple shear stresses are possible, not only one single shear stress. Yeah? For example, here we have the dislocation line. If we apply shear stress along this dislocation line, then it will not move the dislocation. Yeah. However, only when we apply shear stress that is perpendicular to that dislocation line will the plane shift and move, which will make dislocation motion occurs. And eventually, if it goes to the edge of that material, we will have deformation. Okay. To move the edge dislocation, the shear must not be parallel to the dislocation line. It has to be at least with having some angle. Then what will really shift the dislocation line is the perpendicular component of the shear stress. Dislocation move along slip plane in slip direction perpendicular to the dislocation line. Slip direction is the same direction as the Berger vector. Yeah, we have this dislocation line, and we have this dislocation line, and we apply shear stress. This is one up on the top half is to the right, lower half to the left. The slip, the edge here, the dislocation line will move to the right here. So eventually we will have this edge dislocation. When we have screw dislocation, similar like this, yeah. This is the screw dislocation. We will also can have edge, screw dislocation, which will appear as a deformation outside. So edge dislocation line move parallel to the applied stress. Yeah, the applied stress is yes, this one to the right and to the left. The dislocation line will move the same direction as the applied stress here to the right. So at the end, deformation will appear externally, yeah, from the macroscale point of view. Similarly, here at the screw dislocation, the screw dislocation line also move perpendicular to the applied stress. So what about the stress field around the dislocation? So we have this one line dislocation, right? On the upper part, since they are here, especially the planes, is trying to minimize the energy in order to be in equilibrium. Yeah? The upper part, so here you will have a smaller distance of the atoms compared to the field far beyond this dislocation line. So then what we will have is the bonds here are being compressed On the lower part, on the lower part, on the other hand, then we will have that further distance between the uh, between the between the atoms. So on the other, so in different words, that the atoms in the lower part are being stretched. Okay, so in above the dislocation line, we have compression region, while below the dislocation line, we have tension region. Okay, why is there a stress field? Yeah, as I mentioned, the atoms are trying to minimize the energy. The atoms try to relax by trying to achieve their position for the case if there was not a dislocation in the vicinity. If there is no dislocation, so each of these atoms, if there is no dislocation, there will be an atom plane also here, right, in the middle. So since this atom plane is missing, the other two planes on its vicinity try to make balance. Yeah, so that because if it is still empty, then they will have a kind of the energy is not stable. If the energy is not stable, they are in completely in stretch, while in the upper part is in compress. To minimize the energy, then the lower part is trying to close this gap. Yeah. The strain fields around this location interact with each other. Hence, they exert force on each other. For example, here you have the dislocation, line dislocation. The upper part is in compression. The lower part is in repulsion. Yeah. So here the dislocation line is above like this. Similarly, if you have similar dislocation in on this vicinity, which is also similarly upper part is in compression, lower part is in tension, they will repel each other. Um, they cannot move towards each other. So instead, they will move against or away from each other. So edge dislocation when they are in the same plane, they repel each other if they have the same sign, yeah, the same Berger direction. On the other hand, if you have different Berger direction, so you have one dislocation line where the vector is upwards, yeah. So the upper part is in compression. So let's see here. So similar like this. Yeah. On its vicinity, you have another dislocation line whose Berger vectors is directed opposite. Yeah. It is downward like this. So the lower half is in compression, the upper half is in tension. This can they will attract to each other. They can get closer to each other, and eventually they will have their dislocation annihilated to form a perfect crystal. Okay. So when the dislocation have opposite sign, then they can attract and annihilate uh, the dislocation. The number of dislocation in a material is expressed using the term dislocation density. This is the total dislocation length per unit volume, or the number of dislocation intersecting a unit area. The unit are how many millimeters per minute per cubic millimeter, or just how many dislocation per millimeter. Dislocation densities can vary from 1000 per square millimeter in carefully solidified metal crystal. So when it is carefully solidified, means you have less amount of defect, right? But in heavily deformed metals, the number of dislocation density can go up to 10 to the power of 10 per millimeter square. So where do these dislocation come from? What are their sources? So most crystalline material, especially metal, have this dislocation in their S-form state as a result of stress. The stress can be due to the mechanical stress during the treatment of the solidification, or due to thermal stress. For example, when they are cooled suddenly from high temperature, then you can have the material can have thermal stress. So all of these are usually associated with the manufacturing process being used. So it means also by controlling the manufacturing process, we can also control the number of dislocation. So the number of dislocation increases dramatically during plastic deformation. So as we can see in the previous picture here, this picture. So this has a lot of plastic deformation. Basically, this comes from a lot of the dislocation occurring in that material. Dislocations spawn from existing dislocations, grain boundaries and surfaces, and other defects. Now, what is the mechanism for deformation to occur? As I have mentioned many times, it is due to the slip system. So we have slip plane, the plane that allowing the easiest slippage. Usually it has wide interplanar spacing, the highest planar density. The direction of the motion itself, of the slip direction, to the direction where it has the highest linear density. For example, here we have an FCC, a face center cube crystalline structure, remember? So the slip can occur on 111 plane. So this is 111 plane, remember? Close back in 110 direction. The direction will be in 110. So if it were 110, this direction, right? This direction, or this one, or this one. So in total, you will have 12 slip systems in FCC. In body center cube, in an hexagonal close pack crystalline structure, other slip system will occur. Okay. So you have here 111. You can have 111 here also. So 1, 2, 3, 4. You can have 4 111 plane in within one single cube. So if you have 3 direction of slipping with slippage, which is 11 in the 110 directional family. So in total, the slip system will be 4 times 3 equals to 12. So dislocation move with ease on certain crystallographic planes and along certain direction on these planes. The plane is called as slip plane, like this one. It will be the 111 plane. The direction is called the slip direction. In this case, the direction of the slippage could be here, ACF or 110. Another one is also here, 110 direction, ABD, or along this DEF slip. Combination of the plane of slip and direction, we will have slip system. The slip plane and direction are those of the highest packing density. The distance between atoms is shorter than the average. With high number of coordination along the planes are also important. So for example, here in face center cubic, you will have 12 slip system coming from 111 family of plane, in which case then within a single cube you can have 4-1-1-1, right? 1-1-1 here, 1-1 like this, 1-1-1 here, and like that. So 4-1-1-1 planes. The slip direction for each of the plane is 110 family. So 4 times 3, 12 slip system. In body center cubic, you could have the slip plane in 110 plane family, yeah, where then uh, the slip direction is in 111. You could also then have 12 slip system. If the slip plane is along the 211, the slip 211 plane, yeah, with 111 direction, 1 over bar, one direction, then you could also have 12. If the plane, slip plane is 321, 321 plane, then which each could occur 6 times within a single 6 different kind of 3-to-1 family plane within a single body center cube, then you could have 24, sorry, not 6, 8, even 8, 8 times 3, 24 slip system. In hexagonal close pack, yeah, you could have this slip plane 0001 family plane, or 101 over bar 0 plane, and 101 over bar 1 family plane, okay, with this slip direction. So you could have 3, 3, or 6 slip system in different element here. So crystal slip due to a resolved shear stress. When applied tension, yeah, this is resolved shear stress. When we apply an axial tension, yeah, the direction is of course perpendicular, or yeah, perpendicular to the area. Yeah. However, since the plane itself within that crystalline structure have certain angle with this stress, so there will be a resolved direction where part of this, it makes an angle, part of this force can also, will also have direction parallel to this plane. That is what we call as the resolved shear stress. The applied tensile stress is sigma equals to F divided by A. We will have a resolved shear stress of tau R equals to the Fs, the shear force, divided by the As. As here will be this cross-sectional area, not this area, but this, yeah, the cross-sectional area of each individual component that will go in slippage. The normal plane is perpendicular, yeah, to the direction of this resolved stress. So the relationship between sigma and tau R, actually this is already discussed, yeah, in the chapter on mechanical properties. Tau R equals to Fs divided by As. Fs itself is the component of F, which is parallel to the slip direction. Yeah. So it has an angle of lambda. Yeah. So Fs equals to F cosine lambda. Then As here is the area of this component that slips. So the component Ns equals to the A, this area of the axial, where the axial tensile is applied, yeah, A divided by cosine phi. And then the resolved stress equals to the sigma cosine lambda, this one, sigma cosine lambda divided by As, or A divided by cosine phi. The A will cancel each other. So this becomes sigma cosine lambda cosine phi. A condition for dislocation motion that before it deform, the tau R, the resolved shear stress, should be larger than critical resolved shear stress. So this is the condition in order that dislocation motion occurs, such that eventually it will deform. From outside point of view, from external point of view, you will see that the material deform. Crystal orientation can make it easy or hard to move dislocation. Yeah, tau r equals to sigma cosine lambda cosine phi. So we apply sigma here, exactly when the slip plane is perpendicular to the direction of the sigma. So it means we have the lambda to be 90 degrees, and the phi also, the phi is 0 degrees. Okay? The phi is 0 degrees. So cosine of 90 degree is 0. Okay, so it means tau r equals to 0. Lambda, because lambda is 90 degree. Fs, yeah, will be directed perpendicular to this sigma. So when the slip plane is perpendicular to the direction of the axial stress, we will not have deformation. Yeah. So typically, the tau CRSS, the critical resolved shear stress, is in the range between 10 to the power of minus 4 gigapascal to 10 to the power of minus 2 gigapascal. So this tau r will be maximum when the plane is about 45 degree, making a 45 degree angles to the direction of sigma. Okay. And in that case, then lambda will be 45 degree, and the phi is also 45 degree. Cosine 45 degree is half times square root of 2. So if this is being squared, so we will have 1 over 2, right? So the tau r will be equals to sigma divided by 2. If the slip plane is in the same direction or parallel to the direction of the axial stress, we will have lambda equals to 0 degree. Yeah, cosine 0 is 1. However, the phi will be equals to 90 degree. Yeah, the phi will be equals to 90 degree, and cosine 90 degree is also 0. So then when the slip plane is parallel to the direction of the axial stress, we will also have tau r, the resolved shear stress, to be 0. Okay. So if you want a deformation, basically the slip plane of the visa, or you have to pull the material not in the direction perpendicular to the slip plane within the material, or nor in the direction parallel to that slip plane. You have to make a certain angle to the slip atomic plane, yeah, within that crystal structure. Especially the resolved shear stress will be maximum when lambda equals to phi equals to 45 degrees, when the slip atomic plane is making an angle of 45 degrees towards the axial stress direction. Resolving the applied stress on the slip plane, shear stress has to be resolved on the slip plane because shear stress is needed for dislocation to move. Dislocation can only move on slip plane, and these planes are rarely on axis with the applied force. We should resolve the force applied in a tensile test F onto the cross-sectional area A, where the slip is going to take place. Yeah, this is the slip plane, as we have mentioned earlier in the different crystal structure system. Yeah, this is the different slip plane here. Okay. Okay. Any questions so far? Then the tau r is equal to the sigma times cosine phi times cosine lambda. And in order that slip can occur, dislocation motion has to occur. And the condition for this is that this tau r should be larger than tau CRR, the critical resolved shear stress. This is slip in the single crystals. Macroscopically, when do material plastically deform, right, from the mechanical property point of view? This occurs when the stress is larger than the yield strength. Remember, yield strength. How does plastic deformation take place? When dislocation motion occurs. Dislocation occurs when the dislocation inside that material is moving until it goes to the edge. Then you also see it as plastic deformation. What about during elastic deformation? During the elastic deformation, the shear stress is still smaller than critical resolved shear stress. So it means what is being changed is only the distance between the atom. There is no slippage of the dislocation plane. So what planes does dislocation move? The slip planes. So when stress equals to the yield strength, what would be the minimum resolve shear stress needed to act on dislocation to initiate dislocation motion, which will be the onset of yield plastic deformation? So this is the question. So it will depends on the angle, yeah, and the of the between the stress between the applied stress and between the direction of the applied stress and the slip plane at in the crystalline structure. So critically resolved shear stress is the minimum shear stress required to initiate slip. Yeah, this is the term, the critical resolved shear stress. So the tau CRSS equals the sigma y, sigma cosine. Yeah, when we apply vertical sigma, vertical stress, times the cosine phi, cosine lambda. Phi is the angle between the stress and the direction of the slip plane, yeah, and that is maybe lambda, and phi is the angle between the area of the where the axial stress is exerted and the area of the slip plane. Sigma y. So when tau CRS is given and we are asked to calculate the sigma y, so sigma y can be calculated equals to tau CRS divided by the maximum cosine phi times cosine lambda. And as we have seen in the earlier slide, this is maximum only when phi equals to lambda equals to 45 degrees. So in which case the value of cosine phi times cosine lambda equals to 0.5. So the critical resources, the maximum stress, that the yield strength, which is the yield strength before the deformation occurs, usually will be equal to 2 times tau CRSS, 2 times the critically resolved shear stress. Yeah, again, if we review again the stress strain graph, so this region is where the elastic deformation occurs, and the deformation can be calculated according to Hooke's law. Yeah. The strain equals to sigma divided by, the strain equals to the E Young's modulus times sigma. E is the gradient. Or sigma equals to the epsilon times E. So, sorry, sigma, the stress, equals to the strain times this the gradient, the Young's modulus. Then at this direction where yield strength occurs, this is region 1. The hardening occurs, the dislocation motion occurs, dislocation motion is generated. So this is where you will start to have plastic deformation. Then after that is when the stress is, or the strain is beyond this ultimate tensile strength, right? Then you will have necking. Necking will occur and eventually it will break. Yeah. Slip will occur first in the slip systems oriented close to this angle, 45 degrees, with respect to the applied stress. Yeah. So this is the picture of single crystal slip. Okay, let's pause until this